Hadar from Max Planck, Max Planck Institute. Actually, Shahar will join the physics department as a postdoctoral fellow starting in September, I think, so you might see him a lot in the next years here around.
Thank you.
And today he will tell us about black hole collision in extreme slow motion.
Okay, thank you very much. Thanks very much for the invitation. I'm really excited to be here. So I changed a little bit the title of the talk. And this is, I'm going to shred work together with Joanne Kamps from University College London and Nick Manton from Cambridge.
Can you explain the image?
I think we will understand during the talk, but I can return to it in the end. Okay. Good, so the motivation for this work comes from the need to understand systems emitting gravitational waves, specifically the two-body problem in GR, which is a very difficult problem. And I think in this form I don't need to motivate you why this is important and how exciting is this era that we're entering of gravitational wave measurements. So any kind of insight we can get into the two-body problem in GR, which is, of course, there's a lot of great work done by the numerical relativity community, but any kind of extra insight we can get into this problem would be very helpful and interesting. So specifically, if we want to look at the gravitational waveform that's emitted by the coalescence of two black holes, then usually we split the waveform into three parts. So this is, by the way, a figure, a drawing by Kip Thorne. It's attributed to Kip Thorne from, I think, a bit above 20 years ago, and they were planning the experiment. And this is how it describes the process. So there are three phases in the merger of black holes, and this is the signal that he predicts. So the in-spiral phase is governed by post-Newtonian, the post-Newtonian approximation. It's known, and the ring-down phase after the black hole already merged is governed by quasi-normal modes, or by the decay modes of the final black hole. But the merger phase, which is the middle phase, which is governed by strongly nonlinear physics, rapidly evolving space-times, is so a priori we would think that it would be very unpredictable, have these sharp bits here, and actually, when we measured, not all of us, when some of us measured the first gravitational waves, then it was seen actually that this merger phase is actually much smoother than we would have thought.
No, so it's actually, it was predicted by numerical simulations.
Right. Yes. Okay. Right. So it was seen before that the solutions are right. So this is actually, this is the filtered signal, and the numerical simulation is this is the famous quote from the LIGO detection paper. So so numerical simulations and also observations tell us that this actually it's a pretty smooth sewing together of these in-spiral and ring-down phases, and the question is why? Why is this why does gravity behave like that? And maybe some insight can be gotten by the so-called effective one-body framework, which the idea is to map, is an approximate map of the two-body problem in GR, in full GR, to some effective space-time, which is described as this black hole in the center, and some pro-particle moving in this effective space-time. So the idea is to kind of approximate, and then this effective space-time, by the way, doesn't solve Einstein's equations, but its parameters are calibrated by matching it to numerical and post-Newtonian inputs. So so that's the idea of this effective one-body formalism, and so it's not very clear maybe why it's allowed to do this, or why if we do this order by order, why is a correct thing to do to map the two-body problem in full GR to just a one-body problem. In Kepler's problem, we know it can work, and that was the inspiration, but it's not clear why in GR it should work. So we're not going to answer this question today, but we're going to look at a specific system in which this is it is understood from the theory directly why is it okay to do this. Why is it okay to map the two-body problem in nonlinear general relativity to such a pro-particle moving in some effective geometry. Okay, and this is actually possible for this very special case of extremal charged black holes. In that case, it's understood how to do this mapping from the two-body to the one-body problem. And we're gonna, so it's called the so-called moduli space approximation for extremal charged black holes. And this allows us to do an analytic black hole merger. And we will ask what kind of insights this gives us into strong field gravitational wave signatures. So just a slide about extremal black holes. So it's a very special class of black holes with zero temperature or degenerate horizons. They saturate the known bounds on charge or angular momentum. And here we will consider the charge case, Q equals M in general relativistic units, G equals C equals 1. And they play an important role in various different subfields of gravitational physics. So, they're relatively well understood within string theory. They have these enhanced symmetries in their near horizon region, which actually makes them the simplest kind of black hole that there is, in a sense. And they have some special universal characteristic behaviors, such as the so-called horizon instabilities, which I won't discuss if you know about it. And importantly, it's believed widely that near extremal rotating black holes might actually exist up in the sky. So this is not the case that we will consider. We'll consider the charge case, but it's also an important reason to study extremal black holes. So we start with the static multi-black hole configurations, which are a special example of a Majumdar-Papapetrou solution. The Majumdar-Papapetrou solutions are solutions to Einstein-Maxwell theory, given by this very simple formula. So the metric and the gauge and the electromagnetic field, they're all determined by a single scalar function, which depends only on the spatial coordinates because it's a static solution. And this function psi needs to solve the Laplace equation, okay, or the Poisson equation. If you want, you can put a source on the right-hand side. Specifically, if you put a source, so it's kind of maps between electrostatics and Einstein-Maxwell theory. It's a special class of solutions, not all possible solutions. It's a very special class. And if you put a source term on the right-hand side, that's actually a collection of point particles, point charges in electrostatics, then this is your psi, right? This is the solution in electrostatics. And if you plug that back in, what it means from the point of view of Einstein-Maxwell theory is a multi-black hole solution like this, which is static. So you have many black holes just sitting there in space. And the idea is that these black holes have equal mass and charge. So the Newtonian pull of these black holes cancels out exactly with the electrostatic yes.
But is it stable?
You can say it's marginally stable, because the idea is, and you will see why, because the idea is that the energy of this solution does not depend on the positions of these black holes. So you can actually place these black holes wherever you want, and there will be exactly the same energy because these forces cancel out. So, and that's why actually these positions of the black holes are called moduli. This is a term borrowed from field theory, in which we have is a certain configuration of the field that depends on certain parameters, but all these solutions are degenerate in these parameters. So you can actually move in the space of solutions very easily without changing your energy.
So does that mean these, going off of Avi's question, does that mean then that we should expect these things to not be stable in the sense that they could just wiggle around and keep the same energy?
So actually what we will do now is exactly do this. We will give them a little push, and then you will see that if you give them a little bit of velocity, then they will not return to the former state, they will just continue evolving slowly.
So they're not bound at all to each other.
they are not, well,
It's like free particles.
you will see in a second what happens when we start moving them. It's not completely trivial what happens. It depends on how many black holes you have, it depends on what are their distances and velocities. And this is a picture I stole from a paper by Andy and Jeremy Michelson, describing the near horizon regions of this black hole system. So here you have 3 black holes. You can think about extremal Reisner nodes from black holes that are like on the chart. So every one of them has a near horizon geometry, which is a 2-dimensional anti-de Sitter space times a sphere. And when they're widely separated, kind of each one of these black holes has its own throat. But when you start moving them towards each other, the throats join, and so there's a certain region. If you're probing the system at a certain radial distance, then you see one throat, and then when you go closer to each of the black holes, you see its own throat. So this was called by them anti-de Sitter fragmentation. So it's kind of a fragmentation of this throat.
So is there one horizon surrounding all of them?
No, the horizon is down here. The horizon is down here. So these black holes haven't merged yet. From
But once is there an escape from that initial throat?
From this one?
Yeah.
Yeah. Okay. Good. Now let's start moving the black holes. So we want to now promote these moduli to variables. We want to let them evolve slowly in time, but we want them to do it in small velocity. Okay, this was studied in 2 beautiful papers by Gibbons and Ruback and by Farrell and Eardley in the 80s. So what happens? So we want to now move the black holes, but then the solution is no longer a solution, so we need to correct it. Don't need to mind the details too much. I'm just explaining in principle how we know what happens when you start moving the black holes. So we add a correction to the solution, which is order v. We do this perturbatively in the velocity. And then we need to solve for these functions in our ansatz, n and a. And then we plug them back into the action to the full Einstein, Hilbert, Maxwell point particle action. And but we plugged in the solution for this n and a. And then we get an effective action, which depends only on the positions of the and velocities of these particles. I didn't write the velocities, but only on the variables corresponding to the black hole. Okay. By the way, this is a well-known procedure. It's also done in post-Newtonian theory. If you want to calculate, for example, so we can also calculate the 0 pn, the Newtonian effective action, and then we can go to the 1 pn like this. We correct the fields to order v. We plug them back into the action. We get an effective action just for the moving particles we have. Okay, so this is, for example, this is equivalent to the calculation of the Einstein-Hilbert, the 1 pn effective action, which I forgot now the reference. Okay, so we did that, and we reach an effective action depending only on the positions and velocities of the particle of the black holes. And then this effective action looks in this form. So it's proportional to the velocity squared, because we don't have any Newtonian terms. And then we have some coefficients which multiply this velocity squared, which depend on the positions of the black holes. Okay, and by the way, these indices A and B run over all the moduli of the system, which are, for example, for the 2-body problem, we have 2 black holes, and each of them has 3 position coordinates, so it's 6 moduli overall. Okay. Now, so that's the effective action. I can write it down explicitly, but I'm not doing it yet. I just want to stress that there is a very beautiful interpretation of this effective action, since I can think of this as a motion in some effective spatial geometry at a constant speed. Why? Because I can think of it about this part here. So I can think, let me write it.
moves.
So this part here, you can think about it at some speed. This effective spatial geometry with metric GAB. Okay, so this is kind of GAB, DXA, DXB is the line element of this effective geometry. Okay. And how does this effective geometry look like in our case? It looks like this. So actually, it's remarkably, you just use the same transformation as in the Kepler problem. You move to relative and center of mass coordinates. And in these coordinates, this moduli space metric has a very simple form. It has one factor, which is just three-dimensional flat space, which corresponds to the motion of the center of mass coordinate, which we'll forget about for now, because we can just look at the system from the center of mass frame. And there's another factor here, which is not flat, and it has this conformal factor gamma, which multiplies the flat metric, which depends on this relative coordinate r star. Okay, and this conformal factor is given by this expression. Okay, so it's not a trivial thing. You can see when r goes to infinity, r star, sorry, goes to infinity, we go to flat space. So this gamma goes to 1, and we're somewhere about here. We go just to flat space. But when we start moving in, it starts becoming interesting. So this geometry has some throat at some non-trivial radius. And then it opens up into a flat cone of deficit angle pi. So actually, when the black holes are very close together, this moduli space geometry opens up to a flat cone, asymptotically. Okay, it's kind of a cone and the black holes can actually, so as long as the approximation holds, the black holes don't quite merge yet. Because black holes can be very close and still, so if they're very close, then they're somewhere down there on this flat cone in this location in the moduli space geometry. So what's so nice about this moduli space geometry picture? Now we can understand very easily what's going on here in terms of the orbits, the possible orbits. So we can see that we have three kinds of orbits basically. One of them is a scattering orbit, this red line. So these black holes come in from infinity, they interact with these velocity-dependent forces and they get thrown back to infinity. The other kind of orbit is a merging orbit, in which the black holes start moving toward each other, and then they start growing closer and closer to each other, and in the end, their distance grows closer and closer and closer. In the approximation, they actually never merge. But at some point, when they're very, very close, of order v squared in the distance, they do merge and the approximation breaks down. And then the horizons join. So, and there's another kind of orbit, which is this marginally, this unstable, circular orbit. Described by this blue line.
I'm puzzled by the fact that it's supposed to be positive definite, but your gamma can be negative.
No, because mu is the reduced mass, and it can it's maximally 1/4. Yeah, it exactly takes care of the yes. It's for the. So mu is the reduced mass. I think maximally it's m/2.
Okay.
Yeah.
So it works out.
Yes. Okay. Good. Let's see how this looks like from the outside. So this is not an exact picture of all the lensing effects that you can see. That's kind of to give a feeling of what happens here. So if we have a head-on merger, the two black holes start moving towards each other from far away. They move slowly. Then they start going closer and closer, and it takes them a parametrically long time to merge. So they grow closer and closer, and approximately this will look like from far away, like this. So when they are very close, it looks like, from some aspects at least, like the black holes have already merged from the shape of this whole object, but it's still two separated black holes. And from the point of view of this near horizon throats, so the throats start when they're completely separated, they move towards each other, the throats join, and then this joining place kind of goes down and down towards the horizon. This is more of a cartoon, but give intuition to this process. Okay, great. These are all beautiful stories that we understand, at least most of them long ago. And we use this story to calculate gravitational waves. So how do we do this? So actually, the Thorne already understood also in the 80s. So actually, all this paper could have been written in the 80s. So Thorne understood that to use the quadruple formula, you don't need fields to be weak. You actually only need the field to evolve slowly. Okay, but it's hard usually to find in GR systems that evolve slowly even though the fields are strong. I think that Thorne had in mind maybe a slowly rotating neutron star. But nevertheless, this holds also for our system. So you just need to use the quadruple formula. And so this is also understood from the point of view of matched asymptotic expansion. So if you have this small parameter v, you have two separated length scales in the system. One is the natural scale of the system determined by the masses of or charges of black holes, and this defines the system zone. And you have also a radiation zone defined by the length scale of the radiation, L over V. So if you have this separation of scales, then you can find a buffer zone in between where you can match these kind of zones, and this is what gives you basically the quadruple formula. So all we need is to calculate the quadruple. Usually for a strongly gravitating system, it's not an easy task. But for these Majumdar-Petro solutions, it's actually an easy task. Because all you need to do is move to a certain gauge called asymptotically Cartesian mass-centered gauge, and which means that you're in the center of mass frame, and also that your coordinates go asymptotically to Cartesian coordinates. And then you can expand the 0, 0 component of the metric. You can expand, and the quadrupolar part appears at the order 1/r cubed, and you can just read from this expansion the quadruple moment of the static system. Because why are we reading the quadruple of a static system? Because in the system zone, the system is that the field is approximately static. So the leading order is just reading the quadruple of the static system. Okay, and this is the form of the quadruple for any kind of observer. So it depends on R star, the relative distance between the black holes, on phi star, a relative angle, because they evolve in a plane, so they have a distance and an angle. And then these y's are spin-weighted spherical harmonics that encode the dependence of the position of the observer in the sky. So and this is the polarization vector, the right-moving polarization vector for gravitational waves. So this is the expression for the quadruple. We need to plug it into the quadruple formula, and let's do it for simplicity for an observer that sits at the North Pole. So it's perpendicular to the plane of motion at the North Pole. And this will be now the expression for the radiation. Just some coefficient, the reduced mass over R, the numerical coefficient, two time derivatives of this expression, which is again determined by R star, the distance between the black hole, and phi star, the angle. And these are calculated from the moduli space geometry quite easily. Okay, they can be written down even analytically in terms of elliptic functions, or can be integrated numerically very easily on Mathematica. That's something that even I could do. So this is an example of three kinds of orbits. One of them, the green one, is a head-on merger at a certain angle. So you can see so this plane is the X star, Y star plane. So this is the plane in which the system moves. And this is the relative coordinates. So the system moves kind of on a straight line here. So this corresponds to black holes that go towards each other at a certain angle. We have a scattering orbit, this red line. So the black holes move towards each other. They go around each other one time and get thrown back to infinity. And we have this blue line here, which is a merger, but it's non-head-on. So the black holes go around each other a few times, and in the end they merge. And these are the gravitational wave signatures that this process emits. So we have, so this is the green line is the head-on merger. So you can see it starts with a certain value and ends with a different value. I will comment on this in a second.
ring down.
And no, yes, and no ring down. In this case, good question. I would need to think. We do have something to say about the late time behavior. The late time behavior we get is a power law. So we know that after the ring down should come tails, but for this specific merger orbit we don't get ring down. Maybe because the velocity is very slow. It's in this slow velocity approximation, so you don't turn on the ring down mode or something like that. I'm not sure. But the later time behavior, the power law will have something to say. So, and this is the scattering orbit, so we get these two wiggles, and then it decays to a different value. This is because, again, the system comes from some angle far away and goes to a different angle far away. And we have this blue line here of the subcritical, the merger, which is non-halo. Let's discuss the late time behavior of the waveform. So we can see two different effects in this late time waveform, early and late time waveform actually. So one thing we can see is a memory effect, which corresponds to the fact that this initial and final values of the waveform are different from each other. So actually, the origin here on the y-axis of this gravitational wave is completely gauged. So I can gauge it away. I can set it by a gauge transformation to be whatever I want. The only thing that is physical is actually the difference between the initial and final values, and that's exactly the memory effect. So this is one thing that we can see here, and we have a very simple expression for it. But that actually doesn't depend on the fact that these are black holes. That could, if I would also throw pieces of matter that come from some angle and go out to some other angle, I would get the same memory effect. The thing that does depend on the black holeness of these objects is the late time decay. So we can look actually at the late time decay, and this was predicted by Ori a few years ago, that the late time tails around Extremal, Reiser, and Nordstrom should go like this for a multiple number L. And this is the expression that we calculate. And just to highlight what I want is only this. So we get this t to the minus 6 in the late time decay, which exactly corresponds to plugging in L equals 2 in the late time decay. Because we are dealing with a quadruple, that's why we're plugging in L equals 2. So this is a check. Even though in our case, it's actually, there are even later times in which the black holes do merge, and then they emit some additional burst of gravitational radiation, which may be small and maybe not small. But anyway, for these moderately late times, so for these moderately late times, we do get the corresponding, we do get good agreement with these predictions. That's it. I will conclude now. So we saw that black holes at the extreme are simpler, and that's why we like extremal black holes. So it's kind of this system is kind of a toy system in which we can study different questions in black hole physics, which is very controllable analytically. It has some subtleties, but it's on the other side, it's very, very controllable analytically, and we got these strong field gravitational wave signatures from that, and it would be interesting to think of more applications of these moduli space approximations to other questions of black hole physics. Thank you.
These are charged, right?
Yes.
So don't you expect E&M radiation?
Yes, there is E&M radiation. You can calculate it as easily as the gravitational one. Yeah, it's a quadruple electromagnetic radiation. Actually, quadruple electric radiation.
So, for example, if the black holes that LIGO saw were charged, at what level would we have seen them? How much charge would you need to have on these black holes?
Well,
no, this one would be
extreme.
huge. This would be extreme. This you would
And they
destroy.
have zero temperature.
I mean,
The what?
They also have zero temperature, so it's not the ones that you will see.
no, but astrophysically, well, first of all, you can't make Q equal M astrophysically because they immediately get neutralized.
Yeah.
But the LIGO, you can put the tight limits on the lab.
Because we didn't see anything.
Right.
No, I'm not. Just to make sure I'm not claiming that this is relevant astrophysically, but just as a for gravity theory, as it goes to understand strong field wave.
Yeah, but just to follow in this question, since this is an extremal black hole, so I would expect the electromagnetic radiation to be at least as strong as gravitational wave. So it would also affect the waveform of gravitational wave itself. Would you agree? I mean, because the orbital reduction is faster than otherwise.
I don't think that the nonlinear interaction between the electromagnetic
There's
No,
no-
no, humans' energy will be lost from
Ah,
the
yes,
system.
yes.
So the system loses energy and that affects
Yeah.
the orbits.
Yeah.
You did not take that.
Okay, so yeah, both of these effects are of the same order. That I agree.
Right.
But both of these effects are of order v to the 5, and all these energies that we're talking about are v to v squared. So actually, you don't have to take that into account. You can if you want to get better precision, but there are other terms you need to calculate before that, actually. Like the 2pn, that's v to the 4. But if you want, you can do it, in principle.
So can you, in principle, solve the equations numerically beyond the
That's a good
small
question.
v
So
limit?
actually, there was a group that studied this numerically.
Like, is it just so beyond the small v limit? Is it just a bunch of ODEs?
No, I don't know what exactly you're referring to, but I'm thinking about solving the full GR Maxwell equations.
Yeah.
Like the
But-
numerical relativity.
Yeah, what I'm talking about is you have this small velocity limit that you're taking here. Can you go beyond that and still have such a simple problem where it's described
I
by?
don't think so. You can go to higher orders in V,
Okay.
but I don't think that you can actually do. There was a numerical group that was studying these things, and actually, what happened there is that they tried to crank up the charge of the black. So they studied two black holes from rest, and they were near extremal charge, and then they let them fall towards each other and studied gravitational radiation. But when they cranked up the charge, then these black holes just didn't fall towards each other. So that was the thing preventing them from
So
going to
they stay,
extremality.
you say they stay relatively non-relativistic because of the charge?
Well, no, I'm saying that just if they would have given some initial velocity to these black holes, then they can be even more extremal and still reach each other in some time. So that's it's a technical issue. But,
Sorry to interrupt. I guess we have a third last short Blackboard speaker, so maybe you guys can turn.